Okay, good evening, I think, 5 o'clock, everybody. So this presentation, we are going to talk a little bit about the nitty-gritty in PLEXOS. Not massively so. It's not going to be a very long presentation, so maybe we can still save a bit of time. But I welcome a lot of questions afterwards. If you have them, even if they're just about the state of the power system in South Africa, you're welcome to ask questions. So let's get right into it. There we go. We're a little bit delayed. There we go. Okay. So, a little bit about Eskom. We are a vertically integrated, state-owned utility. We are the only utility in South Africa, although we do have independent power producers. We currently have 30 power stations, a nominal capacity of just over 46 gigawatts, 38 of which is still coal. That's a very old coal fleet. Average age is about 42 years across 14 currently operating power stations. And that average age is significantly brought down by 2 very new power stations. So the remainder of the coal fleet is very, very old. And as a result of that, the forced outage rates have been trending upwards historically. So as you'll see here, on the right-hand side, the forced outage rates are in orange, and you'll see forced outages going up to above 20 gigawatts. Okay, we're talking around about a 50% forced outage rate overall across 14 coal power stations. And that is due to a number of things. Age is one contributing factor. Another is backlog of planned maintenance, which is due to space on the system to schedule those outages, maintenance contracts being poorly done, not having enough capital or spares to do the maintenance you need to, and pure sabotage, which has actually happened. Power stations simply getting cut off and spares being stolen. That does happen. So aside from our coal stations, we also have one nuclear power station, which is just under 2 gigawatts. That's Kuberg in Cape Town. We have 3 pump storage power stations. Hydro is more of like a hydro peaking kind of situation. They're two very small stations, run-of-river hydro. OCGT, and that's not gas necessarily, that's diesel operated OCGTs. So ideally, we want to be very low capacity factors on the diesel. But because of the poor performance of the coal power stations, we've seen capacity factors up to about 25% on those diesel OCGTs in the last couple of years, which is obviously not ideal for us. Okay, so to give you an idea, terminology that we tend to use is PCLF, planned capability loss factor. That's our planned maintenance. The forced outage rates, we are talking about what we call OCLF and UCLF, other capability loss factor, or unplanned capability loss factor. So we combine those. Those are reported by Eskom Generation. We combine those to model our forced outage rates. OCLF is generally about 1 to 1.5%. It's a very small number. So in general, we're just talking about the UCLF, the unplanned capability loss factor. That's our forced outage rate. We also model partial load losses. But those are not a full unit loss, so we don't model them in the forced outage rates. We model them as an additional reserve requirement placed on the generators because they don't result in a trip, they just result in reduced capacity. We see quite a lot of partial load losses, and a lot of our poor performance can be attributed to partial load losses, specifically on the air heaters or the water heaters in coal power stations. As I said, the coal power station is our large contributor to declining energy availability factor, EAF. And you can see that quite clearly on the graph here, the black line being our coal fleet and the blue being the total fleet. So yes, the coal fleet is driving performance downwards. The unit sizes of our coal power stations are anywhere between 183 at the lower end to 720 megawatts at the high end. That 720 megawatts is our 2 new coal power stations. They're both 6-pack stations, 720 megawatts per unit. So they are large stations and we get very large units. So obviously, loss of a unit like that is a significant issue for the system. The power stations are all modeled as individual generator objects. We don't model the units as separate generators in PLEXOS. We model the station as a singular generator, and then we specify the number of units. So the assumption is then that all the units in the power station are the same kind of capacity, the same min-stable level, those kinds of things, even though that is not necessarily the case, but the variations are small enough that it doesn't really make a difference. We specify then an annual maintenance rate and an annual forced outage rate. And what we're going to talk about here is sorry, that's a typo. It's actually the 2024 calendar year, so it's projections for 2020. No, it is 2023. I changed it. That's correct. Sorry. Then we also specify the technical operating factors for all the stations. So we're looking at our heat rates, ramping rates, min-stable levels, and all these things are specified per power station. So we try to stick as close to reality as we can. Okay, so what I'm talking about to start off with, this is an ST model run. So this is an hourly model run over a full year. This is using 100 variable sample draws and 100 outage pattern draws. We are using a triangular repair time distribution, which means that we are specifying mean time to repair, min time to repair, and max time to repair, and allowing PLEXOS to do some variability between those things for each outage. And we are using the convergent outage method specifically here. So I'm saying it's an ST, but actually it's an MT parser ST. We're not doing any capacity expansion here. It's just running the fleet as it stands. The model is running for a single calendar year, and I'm reporting the mean across all the samples here. So that's what you're seeing. And we are looking then at the variance between the input data and what has actually been scheduled in PLEXOS, okay? To try and see what the convergence is between the input-output data. For us as Eskom, we try to look for a difference of less than 0.5%. When we start getting above that, the numbers start getting a bit large in terms of energy over the whole year, especially with large units. So what you can see here is that for some of the specific power stations, as we start getting into the very high forced outage rates, and in general this is kind of 55% plus, we start seeing problems, the model struggles to converge between the inputs and the outputs. And you'll notice that the differences range from about 0.5% up to 2.1%. And 2% on that specific power station is around about 750 gigawatt hour over a year. So it is a significant energy difference, and we really do need to try and close that gap in order to accurately model the system. Planned outage rate is significantly better. You'll see there's nothing over 0.5. I have highlighted two specific things here, 0.29 and 0.31. I think there's another 0.3 that I forgot to highlight. Yeah, there it is, station 6. And that's starting to approach kind of the bad end of the convergence, and we try to keep our eye on it when we make changes in order to make sure that they don't start slipping higher up. Now, the reason I'm monitoring both of these things together is because we are modeling the mean time to repairs on a single band. We're not using multiple bands for mean time to repair on the forced and the planned outage rates. We have historically struggled to get convergence in a model when we do multi-band simulation on this. It's something we haven't been able to overcome yet. So we are modeling a single band, a single mean time to repair for planned and forced outage rate. Okay, so basically this presentation is then about the testing that we've done to try and close this gap. To start with, the first thing we did was increase the number of sample draws. So what you're seeing here is 100, 200, and 300 samples. I have not shown you, we've actually gone up to 1,000 sample draws with these things, but it really makes no real difference to what you're going to see here. In some cases, you will see, I'm reporting essentially here now the worst sample, the best sample, and the mean sample across all the 100 sample draws. Worst being on the bottom, worst being on the top end, best being on the bottom end, and mean right in the middle. It's a little orange dot. In some cases, you will see that increasing the sample draws kind of narrows the range a little bit. You'll see that on station 5 specifically. And you will also sometimes see that it centers the mean a bit closer to right in the middle of the average of right in the middle of the worst and best case. But other than that, it doesn't really make any difference to the convergence. We still have essentially the same kind of variation for the problematic stations. Increasing the sample draws beyond 100 really hasn't solved our problem. And so from there, we moved on to the next issue. So we started engaging with Energy Exemplar at this point to say, how can we start to try and close this convergence gap? And one of the suggestions we got was that perhaps we are getting conflicting constraints. We are somehow specifying something in the generator object that is attempting to operate the generator in terms of a constraint and is preventing us from being able to schedule as many outages as we need to. So we thought, let's give it a try. Maybe that will solve our problem. And my colleague, Nikeli Kakaza, modeled a very simple model. This was actually separate to the one that I had shown previously, which is why I'm not showing you my station 1 through 14. All he did was input a single generator with a very high forced outage rate and a sort of fixed demand to try and see if he could get convergence if he then deactivated specific properties of the generator and just essentially just had the forced outage rate and the planned outage rate, maintenance rate specified. So we've got a few different scenarios here. The first one is with essentially everything included that we normally specify. Capacities, min stable levels, VOM charge, all the different things. In scenario 2, we start deactivating the max ramp up and ramp down rates. Scenario 3, we also exclude the units out property and the min stable level. In scenario 4, we're excluding the max time to repair and the min time to repair. So this will then be a square distribution for the mean time to repair as opposed to a triangular, because if you exclude those, PLEXOS automatically assumes a square distribution. And in scenario 5, we then also deactivated the mean repair time. And what you'll see is that essentially nothing has any kind of impact on the model whatsoever except for the repair times, which we kind of thought before we did this, but we thought we would sort of do the courtesy of testing it anyway. What you do see is obviously the difference between the normal outage method and the convergence outage method. This is something we would expect to see just based on the mathematics of how these two things are done. I'm not sure if you're aware of how PLEXOS actually schedules normal versus convergence method outages, because I wasn't at all until Nathan explained it to us. And essentially what happens is that on the normal outage method, what PLEXOS will do is we'll say, I have a mean time to repair, I have a forced outage rate over the year, I know how long a year is, and I can calculate the time between outages on an average based on those numbers. And then PLEXOS will apply some random factor to the time between outages, and then it will schedule a number of outages across the year, which is why the normal method will not always converge, because there is a random factor involved. On the convergence method, what PLEXOS will try to do is it will randomly allocate outages across the year, attempting to then get to your convergence. Now, the higher forced outage rate you get, the more difficult it is to find space where those outages are not overlapping, okay? And this really started to give us some idea of what was going on here, because clearly reducing the mean time to repair will mean that those outages are smaller and will fall into the year without overlapping, okay? So that starts getting us closer to what we wanted. This was playing with the mean, min, and max time to repair. Here we have the most luck and we have the most change across the actual outage spread. This is actually what we have traditionally done in order to achieve convergence. Now, as our forced outage rates get higher and higher and higher, we need to bring that mean time to repair lower and lower and lower to very unrealistic values, sometimes as low as 24 hours in order to try and get convergence. Now, obviously, a 24-hour mean time to repair on a unit of 750 megawatts is completely unrealistic, right? And sometimes 24 hours doesn't even do it, okay? And working on a single band means that if we are adjusting the mean time to repair for the forced outage rate, we are also impacting the maintenance rate. And sometimes we then lose convergence on the maintenance rate. So this is not an ideal solution. It's incredibly time intensive because it requires a run, a change, another run, and a check. It's a very iterative process to try and get to where you're going. And it doesn't actually solve the problem. And finally, we get to what we wanted, which was a very simple fix in PLEXOS that we didn't even know existed. We hadn't even looked at it. The default number for samples per pattern on the convergence outage method is 7, okay? We historically haven't increased this very much. Essentially what this means is that for every outage sample draw that you do, it generates 7 outage patterns, and it picks the best one out of those. I increased this steadily from 7 and up to about 400 samples per pattern. We yield essentially convergence. The 0.6 there on station 5, I will take honestly at this point because it has been a process. I know it's above 0.5, but 0.6 is fine. Judgment calls, right? We all do that. Engineers make things work. We don't really need to get into the nitty-gritty of it. So we were very concerned that this increased number of samples per pattern could lead to severely increased runtimes, especially if we're going from 7 to 400. It does not. We saw almost no increase in runtime whatsoever. There is a small increase perhaps in your parser runtime, although that's such a small portion of the overall runtime that it barely impacts the ST run at all. So for this specific run, we use Connect when we run, so it's sitting on a server. This 1 year at 100 sample draws, 400 samples per pattern, takes about an hour to complete. So perfectly acceptable, great solution. We're very happy. This solved the problem, and it was as simple as finding someone who knew exactly how things were working inside the tool. And sometimes, we all have our different specialties, so it takes a person who's worked with it before, and then increasing that value. So in conclusion, we know that aging plant can result in higher failure rates, and you have to adjust your modeling methods accordingly. As things change, you can't always model the same way. We can't always assume input-output convergence as modelers. I think it's something that we should start checking. It's not a difficult check, it's quite a simple check, and with PLEXOS Cloud, you can pull your input data quite easily. So it's truly worth checking. Small differences of 1% to 2% can make quite a big change in energy at the end. We saw that changing your constraints, increasing your sample draws, didn't really have any effect. Now, I'm going to say that with a caveat because obviously increasing your sample draws from 10 to 100 is going to have an effect. 10 sample draws is not enough. But beyond anything that's statistically significant, beyond about 100 sample draws, you're not going to see a difference. Playing with your time to repair absolutely is going to have an impact, although it might not always be the ideal solution. You might get to something that's unrealistic. But increasing the number of samples per pattern, I think, sufficiently resolved our problem and did it with little effort and no real cost or drawback to us. And that is my presentation.
All right, so I'm holding the mic. I get the first question.
Okay.
Did you end up putting back your multi-bands after you increased the number of?
We have not tried it again yet.
Okay.
We're still running on a single band. Obviously now we're not changing the mean time to repair anymore, so it's not having that impact that we used to see. Currently it's sufficient and doing what it's supposed to do. We might test it again going forward.
And you reverted back on your mean time to repair as well? Yeah, okay. Very good. All right, do I have any other questions?
Hi there, Michael Ball from Varsala. So just taking up on the opportunity to ask maybe more general questions.
Yes, please.
So I think we're at, day 57 now without load shedding?
Correct.
Which is great. But the question I have is, how long will this continue? I think there's been speculation that we...
Is this an election thing?
And we have obviously elections next week, so there's been speculation that we may have pushed our planned maintenance, but in your view, how long do you think this will continue? I mean, based on
just any focus on planned maintenance is going to be the right place to focus. Okay, so even if this has just been a focus on planned maintenance for the sake of whatever it is, I will take it. We have managed to increase EAF at the plant to 70% for the first time in I don't know how many years. I'm hoping that that is a sustainable change. I don't see exactly what could have been done just to patch holes at the point that it was in order to get to 70%. I don't think we are going to suddenly revert to load shedding again after the 29th, although I can't speak to how quickly power stations might deteriorate again after that, whether planned maintenance is going to be kept up or not. It is currently the policy of the CEO. We have a new CEO, Dan Morikane. It's currently Dan and Generation's policy to focus heavily on planned maintenance and take that forward. So, with that focus and with the changes we've seen because of that focus, I'm hoping that that's going to carry forward. And it's also important to note that that is not a change you can make in 2 months before elections. This is a focus that has been placed on Generation 5 years ago, and we are now seeing the fruits of some of those efforts come to fruition. So hopefully it's not just a quick change for nothing. Hopefully it is a sustainable change.
Now, one more question. Thanks for that. Also, maybe one question, you talk about maintenance time, but also I guess one thing really relevant for Eskom is the quality control in terms of the maintenance work. So I mean, are you seeing improvements in that regard as well, that once planned maintenance has been done, you do see improved and long kind of reliability from these facilities?
Yeah, it's hard to it's hard to track that very, very well. So we do see obviously an instant change after planned maintenance is done. You see an increased availability at the power station. The problem is how long do we see that holding essentially? So yeah, look, I think recently the quality and maintenance has improved. The problems that we've seen before have more been that the unit has been out for the allocated time, but the work is essentially not getting done. And that was for many, many reasons. Chief among them was that maintenance schedules were changing quite frequently. And you can't plan a maintenance activity at one power station and then say, oh, we're just going to keep that one on and we'll change it to this one. You don't have the spares, you don't have the right people, you don't have the right plans in place. So you can shut it down for 120 days, but if you don't have all the right stuff, then that's not being done. And more recently, the plans really have been following through. So I would be inclined to say that things are a bit more sustainable than they were previously.
Yeah, Felix from 50 Hertz. Thank you very much for this very detailed presentation. I think when I have a question regarding outage modeling, I will contact you. That's good to know the people who are doing it very sophisticated. What's your feeling regarding the distribution functions that we can use in PLEXOS? Is it enough to capture like the statistics you have on historical data, outage, forced outage durations, mean time to repair, as you mentioned? So I guess we have a lot of, all TSOs, whatever, have a lot of data regarding also the distribution of these kind of parameters. Is it enough to feed it into PLEXOS, or do you have a wish what should be included in order to make it, to increase the your quality in the end of this of modeling the outages?
Okay, yeah, look, that's a very good question. I would struggle to tell you what could be included in addition to what's already there. We have all the data. We calculate statistics outside of the model when we bring them in order to do the distributions, and we have seen, relatively good results from that. It's obviously anything we do as modelers, we're sort of planning into the future, and that is hazy at best. And I sometimes feel that often we focus too heavily on we must get this exactly right when there's no way that our demand forecast is exactly right in 5, 6, 10 years time. There's no way that we can predict exactly what forced outage rates are, what forced outages are going to occur over that time. I mean, just thinking about our nuclear power station, someone doing maintenance, dropping a bolt the size down into the reactor and the unit being out for months on end because of that. I mean, there's no way to predict these kinds of things. So I think the best we can do is to decide what do we want out of this model, what is going to be useful to get out of it, to correctly set up your boundaries saying this is as far as I'm willing to go in terms of detail in order to get useful information, and then to make a call based on that. It's no good sort of modeling absolutely everything in exact detail, knowing that the future is uncertain. So I think it's really up to you as a modeler to use your judgment and say this is sufficient or this is not sufficient. And it varies case to case.